So hello everyone and welcome to today's class. So in today's class, we shall be looking at the normal distribution, where the normal distribution, as we mentioned in our first lecture, is a type of continuous probability distribution. In the last two lectures, we have looked at the binomial distribution and the Poisson distribution. Those two are examples of discrete probability distributions. There is some distinction or difference between number one, how we define the probability in a continuous distribution and how we define the probability in a discrete distribution. For instance, in the case of a discrete distribution, we were talking about the probability of an exact value of x, something like that. So for the binomial, we're having something like this: n choose x, p of x, q, n minus x. So that's the probability of getting exactly x number of successes. Okay. Now, in the case of Poisson, as you've seen, is the probability of getting this number of successes is e minus lambda, then lambda per x over x factorial. So this is true. So this kind of expression is true for discrete probability distributions. You can get the probability of a certain number, an exact number of x. But when we come to the normal distribution, which is an example of a continuous distribution, we'll not be dealing with this. We'll not be working with the exact values of x. We shall be working with a range, the probability that x takes some range of values. So we shall be talking about some interval of x. So for instance, x is between a and b. For continuous distributions, we talk about an interval like this. Okay, an interval. And the best way to look at this interval is to look at the area under a curve. For instance, if this is your curve, which is a straight line, and this is your point A, and this is your point B, then this is the area under that curve, or the area enclosed by the curve. Let's say this is your x-axis. And these two ordinates, these two vertical lines are called ordinates. So if I say that this is a function, if I say this line here is a function of x, let's say y is a function of x, then the value of y at this point, or the value of y given by this, or in other words, these ordinates here, so this is f when x is equal to a. That's the first ordinate here. Okay, and the other one is this line. Then we also have f when x is equal to b. So these two are called ordinates. So when we talk about the area and the curve here, we talk about the area enclosed by the two ordinates, the x-axis and this line here, or this function here. So this is an interval. So in our case, we shall be dealing with something like this, and the probability will be equivalent to the area under some curve after some properties have been met. So for us to smoothly move from a discrete case to a continuous case, and specifically to a normal distribution case, I want us to have a look at a binomial scenario with a certain number of trials and a given probability of success. Then we shall try to increase the number of trials, and then we see how the distribution is changing, or how the curve or the frequency polygon will be changing. So I want us to start by looking at these. Just a minute. So let's consider a binomial scenario. Let's consider a binomial scenario. Where n is equal to 10, and p is 0.5. Let's consider that binomial scenario. I want us to draw a histogram to represent the probability distribution of this scenario here. So let's create a table here, where we have all the values of x, all the possible values of x, 0, 1, 2, 3, 4, 5, 7, 8, 9, and 10. Then here we have the probability of x is equal to the given values there. So the probability values are as shown in this table. And as you can see, at the point x is equal to 5, we look like we have some symmetry, because there seems to be a reflection of all the points. So you see that this point comes here, this point comes here, this one comes down here, and so on and so forth. So it looks like x is equal to 5 is the point of symmetry in this case. Please notice that this binomial scenario here was chosen for convenience, especially the probability value here. I chose 0.5 for convenience. If I chose other values of p, the story might be slightly different. So I chose that one for convenience. So I want us to represent this information graphically using a histogram. So we're going to have a histogram. It's going to be a sketch for me. So I'm going to center the values of x. I'm going to center the values of x. So I have 0, 1, 2, 3, 4, 5, all the way to 10, all the way to 10. Okay, so the histogram looks like this. It's not drawn to scale. I'll show you a well-drawn histogram after this. Then after drawing the histogram, we can superimpose a frequency polygon. First, we mark the midpoint of the top of the bus. Then we connect adjacent points using straight lines. So you will use your ruler to connect these points like that, like that, like that, like that. So these are straight lines. These are segments of straight lines like that, like that, like that, like that, like that. Then for frequency polygon, usually you extend this line backwards like this up to the starting point of the first bar. And you also extend this one to the last point of the last bar like that. So that's a frequency polygon. That's a frequency polygon. Okay. So I want us to compute the area enclosed by the histogram. And I also want us to estimate or approximate the area below the frequency polygon and above the x-axis. Approximate area under the frequency polygon and above x-axis. So the area enclosed by the frequency polygon. So we need to find the area covered by all the rectangles that comprise the histogram. And the sum is 1.00 something. If I round off to 2 decimal places, it will be equal to 1. Ideally, the sum should be exactly equal to 1. Should be exactly equal to 1. If you sum all these probabilities, should be summed to 1. Okay. Now, I want you to tell me what you think about the area that is below the frequency polygon and above the x-axis. If you were to find that area, the area above there, so that area there, the area covered by that. Clearly, we expect that area to be almost equal to the area covered by the rectangles. Almost equal. Maybe it will be smaller. Chances are high that it will be smaller, but we expect it to be almost equal to the area covered by the rectangles. Okay. So I want us to try this experiment with the different values of n. With the different values of n. So I want us to start even with a lower value of n. Maybe we increase it from, we can start with 3, we go to 5, we already have 10, we go to 50, we go to n is equal to 100, maybe 1,000, maybe 10,000. Then we see the kind of graph that we're going to get from those kind of scenarios. So I will take you to RStudio, where I'll be doing the computations. So we are not going to do the computations manually. We shall do them using using some computer software or computer program. So this is RStudio, and I'm going to show you how we can use the computer. You don't need, please remember that you don't need to know how to do this kind of programming, but as if you're interested, is a very easy technique of analyzing data and even getting some nice graphics. So our case number one, we are going to consider a binomial distribution when n is equal to 3 and the probability of success is 0.5. Remember, this probability of success of 0.5 is chosen for convenience. So the first thing I'll do, I'll declare, I'll define a vector here showing all the possible values of x. The number of successes can be 0, 1, 2, or 3 if n is equal to 3. Then I also need to say that the number of trials is 3. Then I have a program here, I have a code here which calculates the probabilities. So for instance, I can calculate probabilities like that. So this is the probability that x is equal to 0 when you have 3 trials and p is 0.5. This here is the probability that x is equal to 1 when you have 3 trials and 0.5 as a probability of success. This is a probability that x is equal to 2 and probability that x is equal to 3. Okay, then I can plot those probabilities, but now I'll not use a histogram, but I'll use a similar kind of graph. So I'm going to do the plotting there. So I'm going to plot. So when I plot those probability values, so this is the graph that we have. So these are the values of x, 0, 1, 2, and 3. Then on the vertical axis, we have the probability. So this is the probability when x is 0, a very short bar here, a very short vertical line. When x is 1, the vertical line goes up to here. When x is 2, the vertical line is the same as this. And then we have this. As you can notice, it is possible to identify the center of this distribution. There's some well-defined center and also something like a line of symmetry. We can draw a line of symmetry around 1.5 here in such a way that the left-hand side and the right-hand side are exactly identical. They're exactly identical halves. Okay. Then I can superimpose the frequency polygon. So if I do that, if I superimpose the frequency polygon, I'll get this kind of graph. I'll get this kind of graph. Okay, so this is a frequency polygon, the blue line, like that. Okay, you notice that if I were to find the area covered by the histograms in this scenario here, it will be the same as summing the probabilities here. So if I just say here, if I sum the probabilities, you'll get that the sum of all the probabilities in the distribution will be equal to 1. But the area below the blue line here, chances are very high that it is less than 1. Chances are very high that it is less than 1 because it's not covering every part of the histogram. Okay, so that's the first scenario. The second scenario, I want us to consider a binomial distribution when n is equal to 5. That is when we have 5 trials and the probability of success is 0.5. So the number of successes are 0, 1, 2, 3, all the way to 5. These are the number of successes. Then the number of trials is 5. Then the probability of success, the probability for each possible value of x, the probability for each possible value of x is given here, 0.03125, and so on and so forth, in such a way that if you sum these values here, you'll always get 1. Then the histogram for that case will look like this. If I draw the graph, it will look like this. So this is when x is 0, when x is 1, when x is 2, when x is 3, when x is 4, when x is 5. It seems like we can get a line of symmetry around here at the center here, around 2.5, at 2.5, in such a way that the left-hand side is exactly the same as the right-hand side. Okay, if I superimpose the lines, this is what you get. So this is a kind of graph that you have. So you have this graph, okay, which is a frequency polygon. So then the one that we did manually in class is case number 3. When you have 10 trials with p 0.5. So when you draw that graph, this is a graph that we already have. You have this kind of graph. This is a graph that we already have. This is the one that we did in the whiteboard. Okay. Then if I increase the number of trials, and you see now, if you have more trials, you may not be able to do them manually. It will take a lot of time. Like when n is 50, you may not be able to compute the probabilities for the 51 possible values of x. So, but using a computer software, it is quite easy, because now I've just listed all the possible values of x. They are 50. Then I declare that my n is 50. Then the probability for each possible value will be given by that code there. And as you can see, some of the probability values are quite small. These are 51 probability values. So these are the first 5, these are the first 4. So like that. So this is 49, 50, and 51. So if I plot the graph there, if I plot that graph, this is what you will get. So this is how your histogram will look like if this were bars, or if you convert these ones into bars. So this is how your histogram will look like. So you will have very small probabilities, very small probabilities here. These are very small values of probability, but the probabilities are increasing. They increase up to a certain point. That point corresponds to the line of symmetry here, which is 25 in this case. Then after that point, they start going down. So you end up with a symmetrical distribution like that. Okay. If you insert or if you superimpose the frequency polygon, you will end up with something like this. If you superimpose the frequency polygon, it almost looks like a smooth curve. Remember, a frequency polygon is drawn using segments of straight lines. And as you can see here, there's evidence that these are segments of straight lines. As you can see, this turn here is very sharp. Even this one here. So these are frequency polygon, but it looks like a smooth curve to a very great extent. Looks like a smooth curve to a very great extent. Okay, which is symmetrical at this point here. Which is symmetrical at this point. Okay. Then if I increase the number of trials, like in this case, I've increased them to 50. If I have not 100 now, if I have 100 trials, the same probability of success, then this is the graph that I'm going to get. I'm going to get these. So this is what you have. So we are interested in the blue line, which now looks like a smooth curve. If I increase even further, let's say to 10,000, to 1,000 trials, then this is the kind of graph that I'll get from there. So these are the vertical lines. They are too close. They are very close. It looks like there's no gap in between. There's no gap in between the vertical lines now. And that's now where the concept of continuous distribution will come in now. Because there seems to be, X is taking all the possible values. The graph tells us that the X is taking all the possible values here. We can't seem to see any gaps there, okay? Then if I draw my my frequency polygon, this is how it looks like. This is how it looks like. Looks like a smooth curve. There are no sharp turns. No sharp turns at any point. Okay, and then here you can see that all the spaces have been covered. So X is taking all the possible values. That's why you can see there's no white space in between there. So if I choose a very large value of n, let's say, let me work with 10,000, and even here 10,000, then I plot. Okay, so when I plot, this is how the plot will look like. Okay, more or less like the first case. Then when I fix the line, the red line there, looks like X is taking all the possible values. You don't seem to be seeing any gaps or any jumps there. Okay, so now that's what brings us to the concept of the continuous distribution. I want to show you all the graphs that we have drawn so that you can compare them. And I'll use a certain function here. So I'm going to repeat this. So if I run this, I want to show you all the graphs on the same page. Scenario, but I want this one to be, let's keep this one at 1,000. Let's keep this at 1,000. So we have this. Okay. So if you draw all the graphs on the same page, this is what you will end up with. Okay. As you can see, this is a rugged line graph, even this one. But as you increase the number of trials, and remember we're in a binomial situation, as you increase the number of trials, the frequency polygon smoothens. When we reach 150 trials, it is fairly smooth. As you can see, the curve is fairly smooth. Now it looks like a smooth curve, not like a polygon. When we are at 100 trials, looks very nice. When we are at 1,000, it is almost a smooth curve. It's purely a smooth curve. It's purely a smooth curve. Okay. So that tells you that, just like we saw that in the previous class, you can estimate a binomial using a Poisson distribution. It is also possible for you to estimate a binomial distribution using a normal distribution. We'll be talking about that a little bit later. Any question regarding that? So you notice that as you increase the values of n, as the values of n increases, then this frequency polygon here becomes a smooth curve, And this smooth curve seems to be a symmetrical curve, which looks like this. So if you increase the number of trials, when p is 0.5, you will end up with this kind of curve, a smooth curve that looks like that. You will end up with a smooth curve that looks like that. And this curve seems to be symmetrical about a point here. So these are your values of x, and these are the probabilities. So we'll end up with a curve like that. So if I go back to the diagrams, if you look at these curves, the first curve here is symmetrical about x is 1.5. And what do we know about x is 1.5 for this distribution? Remember, this is binomial distribution with only 3 trials when p is 0.5. What do we know about this point here? X is 1.5. We know that that corresponds to the mean value. Recall, for the binomial distribution, the mean is given by n times p. So for instance, when n is equal to 3 and p is 0.5, then your mean is 1.5. So this is the 1.5 we are talking about, this point here. So x is 1.5 is your mean value of x. And you notice that that mean value also corresponds with the highest point of the curve. And that's true for even for here. This was when n was 5 and p is 0.5. So the mean was 5 times 0.5, which is 2.5. So this is the mean point here, corresponds to the highest point of the curve. In this case, we had 10 times, or we have 10 times 0.5. So the mean is 5. And the point of symmetry, or the line of symmetry, is x is equal to 5. So that's the mean. The same case here. The mean is 25. As you can see here, the highest point corresponds to x is equal to 25. The same case here, and even here. So you notice that this point of symmetry is the mean. So this point here is the mean. That point is the mean. It also corresponds with the highest point of the curve. In descriptive statistics, this is the most occurrent observation. So this point here, x is equal to 5, we're saying is the mean. It is also the most occurrent. But because now we're in the context of probabilities, we say the most probable outcome, the most probable outcome here. And the most probable outcome is called the mode. So we're saying this point here is the mean. It's also equal to the mode. And again, if you look at the range of x, if you were to arrange all the possible values of x from the smallest, which is 0, or maybe minus infinity, all the way to plus infinity. If you are to arrange all the possible values of x here, then you locate the center, you will notice that this point here is also the center. So it's also equal to the center of the distribution, and that's called the median. So we are observing that if you do this binomial experiment for a large value of n, you will end up with this kind of symmetrical curve, where the line of symmetry is x is equal to the mean, or the mode, and the median. This kind of distribution, a distribution with this feature, which is bell-shaped, this is bell-shaped, has only one point as the mode or value, and is symmetrical about the mean, where the mean, the median, and the mode are equal. This is now what we call the normal distribution. The normal distribution. So I want us to say the following. So we say that this unimodal means with only one mode. This unimodal symmetrical because, as you can see, we can divide it into two identical halves. Symmetrical bell-shaped distribution. This unimodal symmetrical bell-shaped distribution, or bell-shaped curve, is of great importance in statistical work. It is called the normal distribution. It is called the normal distribution. Sometimes it's called the Gaussian. Gauss is the name of the person who developed this kind of distribution, or the one who discovered this kind of distribution. Gauss. Okay. So here we're going to mention the properties of the normal distribution, and we are going to list around 5 of them, 5 properties of the normal distribution. So let's have some introduction before we list the specific properties. So if y is the ordinate of the probability curve, the Remember, what we are calling an ordinate is this kind of, I think I explained that a little bit earlier. So if this is the probability curve, as you know, there is some vertical axis like this. So this is your y. So all these vertical lines here are called ordinates. Huh? All those, if you're able to get those vertical lines, and then this is your x. So these are what we're calling the ordinates. So if y is the ordinate of the probability curve, then the normal probability curve can be plotted from the equation. So if these are ordinates, so if we have ordinates like this, if we have ordinates like this, then as you saw, if we increase the number of ordinates, we'll be able to get up the probability curve by just joining like that. So if we have so many of them, we're able to get a smooth curve like that. So we're saying that if y is the ordinate of the probability curve, then the normal probability curve can be plotted from an equation of this format. So we can plot the curve of y using this function. I hope you are aware that something like this, when you have something like this, is read as y is a function of x. So this is a formula that gives y. So y is a function of x in this case. But now I want to avoid using letter f, and I replace it with another Greek letter called phi. So, but the meaning does not change. So this just means that y is a function of x. But because this y is a probability distribution, or is a density function, then we use this symbol here to differentiate with normal functions like the linear functions, quadratic functions, and so on and so forth. So the probability curve can be drawn using the equation y is phi of x. So which just means that y is a function of x, okay? Where x is a continuous variable. Where x is a continuous variable, that means that x takes all the possible values. X takes all the possible values within a given interval. And generally we say x takes all the values from -infinity to +infinity. So we say that x takes all the values. It can take any value from -infinity to +infinity. And this is what makes the distribution a continuous variable. I mean a continuous distribution, because it takes all the values within that interval. So we're saying that x, if this is your x-axis, this function here is defined for all the possible values of x. It is defined, okay? So this is your y, which is a function of, so we're using phi, y is a function of x, like that, okay? Then we're saying that this one here means that y is a function of x. This is just function of x. So that's how you read it. This means it's a function of x. This is a Greek symbol called phi. Okay, it's a Greek symbol called phi. So you pronounce it as phi. Okay. Then we say that the normal probability distribution, the normal probability, let's say function, is fully defined. By two parameters. So this function here, this is a formula. This is just some formula here. And we shall not define the specific formula in this class, but it's some formula. And we're saying that when x is known, then this formula is fully defined when some two parameters are known, or when two parameters are given or estimated, defined by two parameters, that is mu and sigma. In other words, we are saying that this formula here contains these two parameters. If you remember, in the case of binomial, For the binomial distribution to be fully defined, you needed n and p. You needed n and p. For the Poisson to be fully defined, you need only one parameter like that. So for the normal distribution, you need n. Sorry, you need mu and sigma. That is the mean and the standard deviation. So for the normal distribution to be fully defined, these two things must be known. Sometimes you use the variance, not the standard deviation. But of course, you know that variance is sigma squared. Okay. So these are now the properties of this kind of distribution, of the normal distribution. These are the properties of the normal distribution. Some of them, you see them, you just see them with your eyes. Number one is that the curve is symmetrical, comma, unimodal, and bell-shaped. So that's one of the properties of the normal distribution. So the first property we have said is that the curve is symmetrical, and then it is unimodal, and then it is bell-shaped, as you've seen in our illustrations. The second property is that the values of y, all the values of y are greater than zero, and they approach zero as x approaches infinity. So if you sketch the curve, it will look like this. So this is your x-axis, then we have some vertical axis there, that's your y-axis. So the curve will look like this. So you notice that this is your function. This is your y is a function of x, that curve. So this curve here. So you notice that that curve is always above this line. It is always above this line. But as you approach minus infinity and plus infinity, it becomes very close, but it will never touch the x-axis like that. Okay, it approaches like that. So that's one property. So all the values, so this curve is entirely above the x-axis. That's the second property. The third property is that we can show that the entire area under this curve here, the entire area is equal to 1. And that property is very important because that's what makes it a probability distribution. That's what makes it a probability distribution. Because for a probability distribution, the cumulative probability, if you sum all the possible, if you cumulate the probabilities for all the possible values of x from minus infinity to positive infinity, you should get 1. So that's a very important property. Then it can be shown, and actually in the illustrations that we were having in R, we were able to show that the median is equal to the mean is equal to the mode. We were able to show that these three are equal. Then it can be shown that those three actually are the parameter mu. They are equal to the parameter mu. Then it can also be shown that the parameter sigma is actually the standard deviation of that distribution. Is actually the standard deviation of that distribution. Then property number 5 is a very important feature because this is what clearly differentiates, or is a very distinctive feature between a discrete and a continuous distribution. If you remember, in the case of discrete probability distributions, we were talking about probability of exact values of x. In the case of binomial, in the case of Poisson. But in the case of a continuous distribution, distributions like the normal distribution, we talk about the probability that x takes some range of values. So like here, we are saying that probably that x takes the values between x1 and x2. So we usually talk about something like this. So we don't talk about the probably that x is equal to, let's say, x1. We never talk about that. We never talk about that. We only talk about the probability that x is within those 2 points like that. Okay, and in this case, we say that the probability that x is between x1 and x2 is this area here. Is the area below the curve, and between this ordinate, this is the ordinate phi of x1, and this is the ordinate phi of x2. So the area below the curve and enclosed by that, and of course the x-axis, that's the probability that x is between x1 and x2. Okay. Then property number 5. And this is a very important property because as you've noticed, we have not given the specific formula for the normal distribution. We have not given the specific formula. We only gave a very general function here, that y is a function of x, of course, when you are given mu and sigma. So we shall be avoiding the general formula of the normal distribution, and we shall be using a simpler definition here, by which we shall be denoting by letter z. And we're saying that if we define z as x minus mu divided by sigma, then it can be shown that z has the same normal distribution as the variable y. It has the same normal distribution as the variable y, okay? For every pair of mu and sigma. And this is the variable that we shall be using in our computations. When you want to calculate any probabilities, we shall be using the z and not the probability of x taking some intervals, okay? So this distribution is called the standard normal distribution. So you'll be hearing a lot of standard normal distribution from now henceforth. And then z is called the z-score. So this item here is called the z-score, or the standardized value of the variable, the standardized value. Later on, I'll tell you that z is just the number of standard deviation, the number of standard deviations above or below the mean, or below the mean. So now, instead of having the curve that I was showing you up there, now we shall be replacing the x here with a z like that. Then this is your function now. This is your probability curve, okay, which will be symmetrical again about the mean. So this will be the mean, which is equal to the median and equal to the mode. So we shall be having a curve which is similar to that of the normal distribution, like that. But now instead of having x down here, we have a z. So I want us to look at the properties of the standard normal distribution. The properties of the standard normal distribution. So as we have mentioned, the standard normal is a normal distribution. And that means that it has the properties of the normal distribution. So we can start by saying that since z is normally distributed, the range of z is plus and minus infinity. In other words, z is defined for all the values from minus infinity to positive infinity. And the distribution of z has the properties 1 to 5 above of the normal distribution. Sorry, we can say that, and it has the properties 1 to 5 above. Additionally, so we're saying that z has a normal distribution, so its range is plus and minus infinity, and it has all these properties, number 1 to number 5. Number 1 to number 5, up to this point. But now here we'll be talking about z here, not x, okay? But it has that property. But there's an additional feature of the standard normal distribution. Additionally, it can be shown that for the standard normal distribution, mu is equal to 0 and standard deviation is equal to 1, same as variance is equal to 1. So we're saying that in addition to the above properties, then the mean of the standard normal is equal to 0. In other words, 0 is also the midpoint So Z is equal to 0 is the midpoint, is also the mode, it's the mean. So we are saying this, for the standard normal, for the standard normal, the center here will be 0. So here you have Z, and we are saying that Z is defined for all the values. So we can have, let's mark some ordinates here. We can have the ordinates 1, 2, 3. I need to draw a nice diagram. So -1, -2, -3. So it goes all the way to minus infinity, plus infinity. So this is the mean, that point. So let me try to improve this curve. Usually the curve looks like this. It comes down very fast. It doesn't touch the x-axis, the horizontal axis. It comes down very, very fast like that. So that's a normal distribution. But this curve remains up here, up to infinity. It continues all the way to infinity. Okay. So as I've mentioned there, what I'm calling Z here is the number of standard deviations from the mean. So if I were to have ordinates like this, and even here, like that, we say that this is up to that point. That is one standard deviation above the mean. And this is, on the other hand, here we have the green one, that is one standard deviation below the mean. Then this one, those are two standard deviations above the mean. And similarly, on the other side, we have two standard deviations below the mean, below because of the minus, and so on and so forth. Okay. Then we show that, we say that it can be shown that, and we shall do this a little bit later, it can be shown that, number one, about 68% of the distribution lies within one standard deviation of the mean. It can be shown that about 68% of this distribution, remember this distribution starts from minus infinity all the way to positive infinity. We are saying that about 68% of that distribution lies within one standard deviation of the mean. So that means one standard deviation above and one standard deviation below. So this is what we are calling 68%. That is one standard deviation within the mean. So we're saying that is around 68%. It's not exactly 68%, but we'll show that it is very close to 68%. Then step number, the second note is that it can be shown that about 95% of the distribution lies within two standard deviations of the mean. Two standard deviations of the mean. So this is two standard deviations of the mean starts from here, from this point to this point. So we're saying this area here, that area there, the black one, around 95%. So that means the unshaded part, the remaining part is just 5%. Okay. Then Roman 3 can be shown that about 99% of the distribution can be shown that about 99% of the distribution lies within about 2.5 standard deviations of the mean. About 99%, very close to 100% of the distribution lies within 2.5 standard deviation or 2.5 standard deviations above and below the mean. So we're talking about this point here. So let me use this color here. So this is 2.5 minus 2.5 is from there, and the other one is here. So well, this is what we're talking about, this area here. Okay, about this area here. So we're saying that area there is about 99%. 99%. That is, it is from here all the way to here, 99%. That means the remaining part is around 1%. So we'll notice that, you will notice that again, 50% of the distribution is below the mean, and the remaining 50% is above the mean. So we are saying that this mean line here divides the distribution into two halves, this line here. So we are saying this, if this is a standard normal distribution, we are saying that this is 0.5, which is 50%, and this is the other 0.5, which is 50%. So where this is 0, all the way to plus infinity, minus infinity, like that. Then you'll also notice that for probability values beyond 3 standard deviations are very small. So we say that, let's note that. Let's note that number 5, number 5 is that values of Z more than 3 standard deviations above or below the mean are very unlikely to occur. So we're saying that the probability values, or the probability of Z occurring beyond plus or minus 3 is quite small. So we're saying that these probabilities here, because we are saying if this is the curve, we have already said that 95% will be here, 2.5. 99% will be here, minus 2.5. So you notice that 3 is here, minus 3, and the other 3 is here. So we're saying the remaining probability here, the one I've shaded, and the one that will be here, all the way to infinity, we're saying that those probability values are quite small. The ones I've shaded in black. So the remaining probability is very unlikely. Those are very unlikely events. So that's the standard normal distribution. And the probability values, these are how we compute the probability values, number 6. So we compute the probability that Z is greater than Z1 and less than Z2 is given by the area under curve, the area under the standard normal curve between the ordinates phi of Z1 and phi of Z2. And this area is always obtained using tables. Area is obtained using some tables known as using the standard normal tables. Using standard normal tables. So using standard normal tables. So as you know, area under curve is obtained using integration, using calculus. But now we shall not be using integration in this class to find the area between two given points. We shall be using some tables which are the areas have been calculated and rounded off to around 4 decimal places. So I'm going to display to you, but before I display the tables to you, this is what we are saying in that point. If this is 0, this is Z, and then here you have Z1 and Z2, then the probability that Z is between Z1 and Z2 is this area here. That area. So this is the probability that Z is between those 2 points. So for continuous distributions, we talk about an interval like this. We talk about an interval like this, not a specific point. So let me display the standard normal table so that we can familiarize ourselves with them. So this is an example of the standard normal tables, and they are giving values of Z. So in this column here, we have Z. As you can see, the definition of Z is X minus mu over sigma, just like we said in our class. And it's giving values of Z from 0 all the way to, it's supposed to go all the way to infinity, but we are stopping at this point because we have said the probability of a value of Z which is beyond 3 standard deviations, beyond 3 standard deviations is usually very small. So these kind of tables, they are giving probabilities from, they're giving this kind of probability that Z is bigger than 0, but less than some Z value here. So this is the point we're calling Z1. And we're only taking the positive side. We're only taking positive values of Z. If you want to get the negative, if you want to work with negative values of Z, you read here, corresponding area for deviations below the mean can be found using symmetry. So for instance, if you have X is equal to, Z is equal to 3, it's the same as when this value is minus 3. So the area from 0 to a 3 is the same as the area from 0 to a minus 3, the same. So that's the concept of symmetry, and that's what we shall be applying. So these particular tables are giving you areas. They're giving you areas for probability that Z is bigger than 0, but less than some value here, positive value of Z here. For instance, if you need probability that Z is bigger than 0, less than 1, it means that you're talking about this value here. You're talking about this area. It means that you're talking about this area here. So you're talking about 0, then you have a 1 there. So between 0 and 1, that's the area you're talking about. And that probability, you just read it from your tables here. So you come to your tables, look for Z is equal to 1. So this is the area here. So the shaded area in my diagram here is 0. So this area here is 0.3413. Remember we said that from this point here all the way to infinity, it is 0.5. And the same case from this point all the way to minus infinity is also 0.5. Okay. So if you need, if I need this area here, this is 0 and this is minus 2. If I need that area, then that area is exactly equal to this area. Is exactly equal to, using symmetry now, is exactly equal to this. 0 to plus 2 is the same as 0 to minus 2. So I'll just come here and locate Z is equal to 2. So this area here will be that. It's also equal to that. It's also equal to that. Okay, so that looks like straightforward. So if you have something like, let me put the decimals now. If you need something like probability that z is bigger than 0, less than 2.78, less than that. So the sketch is always good. It's always good you have a sketch like this. So 0 to 2.78. So you just come to your tables, look for 2.7. 2.7 is here, and 2.78. Remember, these are the decimals, all the way to 9. So you have the value is the required value is this probability value, this number here. So the required probability value is this number. So this is 0.4973, and you can do that for any decimal value. But now you might be asked to find this something like this, the probability that you may want to find the probability that z is bigger than 2.3, for instance. So this is what we are looking for. This is 0, then you have 2.3 here. I'm shading the required area. This is it, all the way to infinity. All the way to infinity. So that's the area that you want. So there are tables that can give you this kind of probability. There are tables that can give you this kind of probability. But if you are using this kind of tables, and it's always advisable that you just use one type of table so that you don't have like 3 different tables. So if you're using this kind of tables, you will read out, you will get from your tables, you will read from your tables this area from here up to that. You will get that area. So you will get the area from your table. So you'll go to 2.3. 2.3, this is the number. So this is 0.4893. So that is the probability that z is bigger than 0, less than 2.3. But now we need the remaining area. So the remaining area here, this area here, will be given by the total area from here all the way to infinity, which you know is 0.5, minus the area from here up to here, which is here. So the area shaded in red here will be 0.5 minus 0.4893. So the difference between those 2 points or those 2 values will be your required probability. So 0.5 minus 0.4893, which is 0.0107. So the area that the probability that z is bigger than 2.3 is 0.0107. And you'll do the same if you are working on the negative side. For instance, if you're working on the negative side, you might get a question like this. Find the probability that z is less than minus 2.15 minus 2.15. So it's always advisable you sketch. So if you sketch, this is what we are looking for. So this is 0. This is minus 2.15. So you're looking for the area below. You are looking for the area below. Okay. So your tables will give you the area from 0 to minus 2.15. So using the symmetry concept, you will come here and look for 2.15. 2.1 is here. 0, 1, 2, 3, 4, 5. So this is a value. So the area from 0 to minus 2.15 is 0.4842. That area. And we know the area from here all the way to minus infinity is 0.5. So the blue area, the area shaded in blue will be, so this area here will be 0.5 minus 0.4842. 0.5 minus 0.4842, which is 0.0158, and so on and so forth. You can also be asked to find area like this. You can be asked to find something like this. You can be asked to find something like this. You have here minus 1.8, and here you have 2.0. So you need this area here. You need that area. So that means you're going to get this area from 0 to 2. Let's say this is 2. What? 2.0. From 0 to 2.0, where the area will be given by this. I'm coming to you, Valentine. So 2.0, then 0 to minus 1.8. So you will use this value. Then you add the two probabilities. So you take these ones, you add them. So this is 0.46. So this is 0.4641, and this is 0.4772. You add the two. When you add the two, that's the probability that Z is between this point and this point. Okay. But sometimes you find that you have something like this. The 2 points are on the same side of the half, on the same half. So you have, let's say you have something like this. This is -1, and this is -2. So you want this area. You need that area. Okay. So this area, you will get it through subtraction. So from your tables, you will get the area, the larger area, of course. The larger area is from 0 to -2. 0 to minus, you'll get that area, the entire of that area. Then you'll get the smaller area from 0 to -1. Then you subtract. You subtract the two to get the area shaded in blue. So any questions about that? So this marks the end of today's class. For those who have not finished the class exercise, you will send me the answers through the private messages. So thanks. Let's meet next week.